Hey folks, this is Dr. Humston, and we made it to Chapter 2. This is Atomic Structure and Radioisotopes. Today we're going to be looking at Section 2.1, Elements and the Structure of the Atom. So we know by now that chemistry is the study of matter, and we're going to find out that all matter is composed of atoms. And then also your textbook says matter consists of elements and compounds. Okay, so I want to pause here and think about what the difference is between an element and a compound. Okay, and I suspect you have an idea of this already, but I want you to try to define it for yourself. So what is an element? And I've given you two examples, right? Carbon, C, and sodium, Na. These are examples of an element. So in your own words, I want you to come up with a definition for an element. And before we move on, let's think about compounds. What is the definition of a compound? Here are some more examples. Glucose, we see C here, but it's C6H12O6 this time. And salt, NaCl. So here sodium was Na, sodium was an element, Na, and salt, NaCl, is a compound. Okay, so at this point you should have some ideas. I'm going to reveal to you my definitions, the textbook definitions, which I want you to know, but make sure that yours and these line up. You don't have to have it exactly the same, but the same idea. So an element is a substance composed of only one type of atom. Okay, so this chapter is all about atoms and atomic structure, and here elements are only one type of atom, and it cannot be broken down. Now, a compound is a substance composed of two or more different atoms. And the different here is key, as we'll see eventually. And these two or more different atoms are held together by chemical bonds, and thus they can be broken down into elements by chemical means. So this chapter will be all about elements and atoms, and compounds we will begin to look at in the next chapter. So when we start the next chapter, be prepared to see this exact same slide, and we'll be focusing then on part 2. So this whole chapter is about elements and atoms, and section 1 is specifically about elements and the structure of the atom. So what is an atom? An atom is defined as the smallest stable component of matter. And the original word, atomos, meant like undividable, something that you cannot break down, which is kind of ironic because now we're going to talk about subatomic particles, the particles that atoms are made up of. So it actually can be broken down, but that was not known until recently. But now we have a definition of atoms that is the smallest stable component of matter, and that we can actually have different atoms for different elements. But these subatomic particles are now all the same. And there are now even more fundamental particles that have been discovered that these subatomic particles are made of. So who knows where that ends? We're not going to go back and change the names of things. So that's what an atom is, and we're going to talk first here about the subatomic particles that make the basic structure of the atom. So we have the proton, the neutron, and the electron. And we can reveal some information about them: their charge, their mass, their relative mass, and location within an atom. So first look at the proton, okay? Protons are positively charged. They have a mass of 1.627 times 10 to the minus 24 kilograms, but that is a very small number. Let's just call it 1 or 1.007. It's located in the nucleus, the center of the atom, which we'll get to again shortly. Neutrons, next, also in the nucleus, but they have no charge. They are neutral, approximately the same mass as a proton. As far as we will treat them, these are the same. And the third subatomic particle is the electron, which is negatively charged, the charge of -1. It has a mass approximately 2,000 times less than the other two. So the relative mass is 0.000559. It's found outside the nucleus. So we can characterize these subatomic particles by their charge, by their mass, and by their location. So where are they found? Now, let's take a look at these units. And let's start with mass. So the gram is the base unit for mass. Kilogram is also often used in science as that's actually the SI unit. The standard international unit is the kilogram. Um, and we get these tiny numbers, right? Remember, times 10 to the minus 24 would be 0.00, and we're going to have 23 zeros, and then 167, dot, dot, dot. So 23 zeros in here, grams, right? Super tiny, hard to talk about, even with scientific notation. And so instead, we make up a new unit called an atomic mass unit, AMU. And instead of saying 1.627 times 10 to the minus 24 grams, we'll say a proton is just equal to 1. That makes our life easy. Let's look at the charge, right? Proton is +1, electron -1. Beautiful, easy. I love it. That is a made-up unit, just like AMU, right? The charge, ±1, is actually 1.602 times 10 to the minus 19 coulombs, where coulomb is the standard unit of charge. But instead, we call this the elemental charge, and now we can talk about +1, -1, right? So here, we can say this again, we make up units to make our lives easier. We're going to encounter this more times, right? So we don't want to say things like 1.66 times 10 to the minus 24. We'll just say 1. We don't want to say things like 1.602 times 10 to the minus 19 coulombs. We're just going to call that 1. So I want to take a brief moment to talk about the history of the atom and also use this as an opportunity to talk about scientific theories. So, or models, right? Our ideas about the atom have definitely changed over the years. Um, the Dalton model in the early 1800s was the idea that the atom was simply a solid sphere. So there are no subatomic particles. There's nothing that an atom can be divided into. There are different elements, but it's just a solid sphere, and they're different. We don't know how. That lasted for quite a long time until the discovery of electrons in the late 1800s, and J.J. Thomson, the J.J. Thomson model was called the plum pudding model, where there was just assumed there was the mass of positive charge throughout the atom, and electrons were scattered throughout the spherical cloud of positive charge, as like plums in a pudding, right? That did not last very long before Rutherford and the nuclear model, only 7 years later. This was actually a really interesting experiment that was done called the gold foil experiment. I'm reading it right here. So Rutherford in his lab fired positively charged particles called alpha particles at a thin sheet of gold foil, and most of it passed straight through. So that kind of eliminated the plum pudding model, right? Because if they're shooting positive charges at a large spherical cloud of positive charge, then there would be interactions and the positive charges would be bounced away or deflected. What happened was most passed through with little deflection, straight through, and some deflected at large angles. This is only possible if the atom was mostly empty space and the positive charge concentrated in the center. Um, what they said at the time was that it was like shooting bullets at a piece of paper and having some of them bounce back. So the nucleus, as it's now known in the center, was very dense, and it could cause the positive alpha particles to bounce away at large angles. So this was the discovery of the atomic nucleus. It did not explain how the electrons were organized around the nucleus. For that, it only had to wait another 2 years, from 1911 to 1913, and the Bohr model is what most people probably think of today, which is a positively charged nucleus in the middle and electrons orbiting in different orbital levels around the nucleus. And this was good for about a decade until the quantum model, and Erwin Schrödinger in the 1920s stated the electrons do not move in clear set paths around the nucleus, but are probability waves that exist as a cloud or orbital around the proton, which is beyond the scope of this course, but it should be said that for almost 100 years now, this is still the model. So there's a lot of activity in about 25 years, and now this is what we believe to be the best way to describe the model, or the atom today. So this gives us a great example of how scientific models can change over time. And they change when new evidence is presented. And new evidence leads to new models. Okay, and a model then is a way to think about a phenomenon or think about the world. So a theory is an explanation. It's a model. It tells us how to think about something. I should add, it is best when based on evidence and leads to predictions. Now contrast this with a scientific law. A law describes, it's a description, and a theory is an explanation. Okay, so we might have a description for how nature works, but have no idea why. And that's where a theory comes in. A theory tells us why or explains it. Okay, so we're mostly gonna kind of combine these last two models when we talk about atoms, and this is kind of how I want you to start to think about what an atom, atomic structure, is. And in the next video, we will start with this slide.